Good afternoon and welcome to today's EHS Today webcast, Calculating Safe Distances and Application of Presence Sensing Devices, sponsored by PILS. My name is Stephanie Valentic, Associate Editor of EHS Today. Before we begin, let me explain how you can participate in today's presentation. First, if at any time you are having audio difficulties or slides are not advancing, simply hit your F5 key to refresh your webcast console. If you have any technical difficulties during today's session, please press the Help button on your player console to receive assistance. This webinar technology allows you to resize the presentation by clicking the Maximize icon or by dragging the lower right corner to enlarge the window. We welcome your questions during today's event. In order to submit your questions to today's presenter, simply type your question into the question window on the left side of your screen and hit the Submit button. We'll be answering as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send me your questions at any time and we'll add them to the queue. Please also be aware that today's session is being recorded and will be available on the EHS Today website within the next week for you to review. You'll be notified by email when the archive is available. On your console, the PILS logo is hot-linked. If you would like to visit their website during this webcast, you can click on the logo and a new window will open. This will not take you out of the event. And now I would like to welcome our presenter. Dan Rossau has a degree in electrical technology from Henry Ford Community College and has been certified as a certified machinery safety expert. Dan has nearly 10 years of machinery support and services in industrial automation applications. He has been with PILS Automation Safety for over 3 years as a safety engineer and technical trainer. Dan, the floor is yours.
Thanks, Stephanie. So today our presentation is going to be on presence sensing devices and basically stop times calculations. So we're going to look at a couple of standards for presence sensing devices. We'll go through some different examples of safe distance formulas and some different stop time techniques. The two main standards that we typically use for looking at stop time analysis is ANSI B1119 or ISO 13855. Today we're going to primarily focus on 13855, and within 13855 you can use different types of technology such as light curtains, laser scanners, safety floor mats, two-hand controls, or even safe vision systems. A few of the applicable standards that we look at are 13855, positioning of safeguards with respect to the approach speeds of the human body. We also have 13857, safety distances to prevent danger zones being reached by upper and lower limbs. Those can also be applied. We have an IEC TS 62046, application of protected equipment to detect the presence sensing of persons. It typically is used for the design of the presence sensing device. Then we also have ANSI B1119, performance criteria for safeguarding. Here we do have several different acronyms that do represent presence sensing devices as a whole. So in industry, you may see one of these multiple acronyms. Here we have ESPE, which is electrosensitive protective equipment. Simply comprised of a sensing device, a control monitoring device, and some kind of signal output. Another acronym you might see is AOPD, Active Optoelectric Protective Device. Here, it's another device used to interrupt light beams, such as a light curtain. Or you might even see AOPDDR, Active Optoelectronic Protective Device responsive to diffuse reflection. In other words, the reflection of light while being used in a laser scanner in 2 dimensions. Most of the light curtains, safety scanners nowadays do have what are called OSSD outputs, which are solid state. They are used with the machine control. They are typically transistors on the output, very similar to a normally closed contact, if you were to relate it to a dry contact. when it comes to light curtains, we have different types of applications we can apply light curtains to. So here we have what's called blanking. So with a specific type of light curtain that allows blanking, you can either have a fixed number of beams that are blanked in a specific location, or the blanking can also be floating, where you have maybe two beams that are blanked and it just floats throughout the up and down the light curtain throughout the application. We also have light curtains that allow for muting applications, virtually for materials to flow in and out of work cells without having to disrupt the workflow through like an interlock guard. So in this case, the material is able to pass through the light curtain following a sequence of sensors that disable the light curtain to allow the material to pass through, but the safety function of the light curtain is still active. So the typical application for this is either through an X pattern, as you can see there in the top left, or if you look at the bottom right corner, there is a 4-beam type setup that can also be used. And there's also proper examples of light curtains or optoelectronic devices that can be used in safety applications. In this example here, we see a standard light beam being used as a protective device to stop this roller. In this case, this is not an approved sensor to be used as a safety object, a safety function. We also have to deal with the proper installation of our safety-rated devices. We shouldn't have the ability to reach behind, around, over, or even crawl underneath it. So the proper mounting is definitely required. We also have to worry about the stability and possibly the detection of where the presence sensing device would be. In this example here, you see we have a vertical light curtain, but once the person walks past the vertical light curtain resets. We need to be able to detect people on the inside of the cell or inside of a loading area, just as long as walking into the cell. In this case, they have actually cascaded 2 light curtains, a horizontal and a vertical. That way detection is made and the machine cannot start while a person is inside the cell, loading the machine. So here we also have to worry about our proper installation as we were discussing. In this case, you may be able to reach around the light curtain into the cell, but we also need to maintain what we call a safe distance. So if the light curtain may be too close, we may have to move it away from the cell. Along with the proper installation, here you see the light curtain can be easily removed. In a normal application, light curtains should be fixed in place and not be easily accessible, be able to be tampered with. As you see here in this example, we have an automobile line. We have 2 different zones in this area where you can see where the arrows are pointing. We have an area where somebody could crawl through from one zone to the next. If you look very carefully along the very edge of that cell, you can see a series of light curtains that have been cascaded to detect somebody walking in and while they're standing on the platform. Actually, on the other side of that plastic curtain you see, there is another set of vertical light curtains that would detect a human from crossing from one side of the cell to the next. But here, we need to be able to not be able to climb on or crawl under the light curtains. You see the 2 holes where those guardrails are. You could actually crawl through those holes on the guardrail. You could easily crawl from one cell into the next and not be detected by the presence sensing device. So being able to be detected and allow easy access to the cell is not permissible. So here, and again, as we were talking, as I mentioned earlier, once you, in this case, you see a vertical light curtain. But once the light curtain is broken and you walk past the light curtain, the machine could be reset. So we need to have some kind of detection on the inside of the cell. So in this case, they're using a combination of a laser scanner and a light curtain within the detection area. That way, if the light curtain is broken, it stops the machine. Or if you're inside the machine loading it, it would also detect you. In order to calculate safe distance, we can look to ISO 13855, where we have different types of approaches we can use to determine our safe calculation distance. We have a vertical approach, which is referred to as our normal, where here we have a beta factor of 90 degrees. In this case, it's 90 degrees from the floor. Also referred to as the perpendicular approach. We have an angular approach, typically works from 5 to 85 degrees, and a parallel approach, which is parallel to the walking surface, which our beta is equal to 0. So here, depending on the angle and the placement of the light curtain, will determine the stop time and the safe distance for the application. So we have a basic formula that we use for any type of stop time calculation. So as to their safe distance, that's the minimum distance we need to be from point of the hazard to the light curtain, which is equal to K. K is an approach speed. It'll always be a constant. E is going to be a combination of the overall stop time of the system, which includes the response time from the present sensing device, response time of the control system, and the overall mechanical stop time of the device that's being stopped. Then that is added to what we have our C factor. This is an additional distance depending on the design and installation of the present sensing device that you are using. So our approach speeds for K, according to 13855, we're going to use 2,000 millimeters per second if unhurried, reaching in with an upper arm or an upper limb. Our normal approach speed would be, for walking, is 1,600 millimeters per second. The other thing that's going to be dictated out is we're going to have to look at the resolution of our present sensing device. The resolution is dictated by D. Here in this example, you can see some very common resolutions. So a finger detection is a 14 millimeter, a 30 millimeter is a hand detection, and anything beyond 40 millimeters, body protection. When we look at the total stop time, we can look at this graph here. You can see the white area is comprised of normal running. You'll see the red section is the response time of the present sensing device. The yellow area will be the machine control response time, so a safety relay or a safety PLC response time. And then once the output of the safety device's response, machine deceleration will take a total amount of time. The total stop time is the present sensing device, stop time, the control system, and mechanical deceleration until it reaches 0. So we can start looking at some of the different approaches. So in this case, we're going to look at the approach speed and depth of penetration for the perpendicular approach. So in this case, the light curtain would be vertical. According to 13855, if we look at the different resolutions, so in this case, a resolution that is less than or equal to 40 millimeters. If we look at the very first calculation formula is S equals 2,000 times T plus 8 times D minus 14. This is where if you were standing from anywhere from 100 millimeters to 500 millimeters away from the object. The 2,000 millimeters per second accounts for arm speed. If we are greater than half a meter away, we can use 1,600 times T plus 8 times D minus 14. If the resolution of the present sensing device is between 40 and 70, we use 1,600 T plus 850. In this case, our intrusion factor, our C factor, is an automatic 850 millimeter constant that is added. They also give us some suggested mounting heights where the lowest beam should be no lower than 300 millimeters. And the highest should be at least 900. Then you can get into multi-beam systems where depending on if you have 2, 3, or 4 beams, there's suggested mounting heights there. Then if you have a single beam system, you have 1,600 times T plus 1,200. And a suggested mounting height of 750 millimeters off the ground. We can start doing some examples based off some given factors. So here we have a type 4 light curtain. Our resolution is 30 millimeters. Here, based off the calculation for over on stop time, they have given us a measured factor of 125 milliseconds. So what we need to do is verify the current safety distance. So the current safety distance that they have on this machine is 400 millimeters. So we're going to select, based off the current safe distance of 400 millimeters, the 2,000 times T plus 8 times D minus 14. Here we can see we have our K times T. We have 2,000 times 0.125, which crunches out to 250 millimeters plus 128. We have our 30 minus 14 times 8. So if we add the 250 and the 128, we get 374 millimeters. 378 millimeters. So based off our current safe distance, our safe distance is sufficient. So our current safe distance of 400 millimeters is sufficient. Here we can go into another example here. Our resolution is 80 millimeters. We're still using a type 4 light curtain. Our total stop time that they're giving us is the machine and the control system is 100 milliseconds. The response time of our AOPD is 50 milliseconds. And our current safe distance is 500 millimeters. In this case, with our resolution being larger than 70 millimeters, we can assume that it's a multi-beam system. So we're going to use the equation 1,600 times T plus 850. So if you look here, we have our 1,600 times our 100 milliseconds and 50 milliseconds. Those two get added together, plus 850. So we have our 240 plus 850 equals a total of 1,090 millimeters. Our current safe distance determines not to be sufficient. So to resolve this issue, there's one of two ways you can do it. You can either, one, move the current light curtain with the resolution of 80 millimeters back to the safe distance of 1,090 millimeters, or you can try to increase the resolution on a different light curtain to possibly have a safety distance that might be shorter. Here we're going to look at the parallel approach for light curtains. here, based off the safe time, stop time formula, we're going to use 1,600 millimeters per second times our total stop time. But C is, in this case, has changed to 1,200 millimeters minus 0.4, and then in this case, H is the height of the protected field off the ground. They recommend that a light curtain be no higher than 300 millimeters if you're going to use it on the horizontal plane for the parallel approach, because what starts to happen is people can crawl underneath the light curtain at higher distances, possibly get closer to the hazard and reach up through the light curtain to the hazard. Also, when you have a light curtain at roughly 300 millimeters, it's more likely to hit somebody's shins and be detected. The higher you raise that light curtain off the ground, the less likely it's going to detect based off your step into it. So let's say if you had it mounted roughly 800 millimeters to a meter on an average male, it's about waist height. So you could easily be nearly 1 meter step in before the light curtain even detects you. You'd be detected underneath the light curtain. So here we have a type 2 light curtain. Current height is 500 millimeters. We have a total stop time that was measured of 200 milliseconds. Our current safe distance is 1,000 millimeters. On a parallel approach or a horizontal light curtain, safe distance is taken from the furthest beam from the hazard. So that's where that 1,000 millimeters comes from. It is the furthest beam from the hazard. Here we're going to have our 1,600 milliseconds, 1,600 millimeters per second times our 200 milliseconds. In this case, we'll have 1,200 minus 0.4 times 500. So when we ultimately crunch our numbers, we'll get 320 plus 1,000. So our total safe distance will be 1,320 millimeters. Our current safe distance is not sufficient. Yet again, we can either get a longer light curtain, that is 1,320 millimeters, or you might be able to go for a tighter resolution, or lower the light curtain to where it could possibly detect you earlier. We also have our angular approaches. So depending on the angle of the light curtain will depend on the approach technique that you use. If you are plus or minus 30 degrees from the parallel or the horizontal light curtain, you use the parallel equations. If you are plus or minus 30 degrees from the normal approach or the vertical light curtain, you use vertical light curtain equations. But in this case, S is the closest beam to the light curtain or the height of the hazard. Whatever the closest beam to the hazard is, that is your safe distance. Here we have yet again our parallel approach, 1,600 times T plus the 1,200 millimeters minus 0.4 and the height of the light curtain. Yet again, the safe distance goes to the furthest beam, and the lowest beam to the ground is the height of the light curtain. So we have to maintain our safe distance all the way around the machine, just like we see here in this example. So depending on where the hazards are, the stop time. So depending on the associated hazards within a cell, in this case we have a light curtain all the way around. The S may be different on one side than it is the other depending on the closest hazard. But we still need to be able to maintain our safe distance for all hazards inside of a cell. So here, one thing we can start doing is that we need to maintain our safe distance. But in this case, we're going to look at the height of the light curtain also. Just like a guard, you can possibly reach over a guard into a hazard. The Same thing can happen with a light curtain. So here, we have a type 4 light curtain. The height of the top beam of the light curtain is at 1,000 millimeters. Our resolution is 14. Our stop time measurement was 125 milliseconds. Our current safe distance is 1,000 millimeters. Here, our resolution is less than 40 millimeters, so we're going to use 14 minus D. It should be 8 times 14 minus D. And what happens here is we have our 14 minus 14 is a 0, so ultimately we are going to have 1,600 times 0.125 seconds for 200. But here, we use 1,600 in our initial calculation. Well, since our S ended up being less than 500, we must now go over to the 2,000 millimeter calculation. Is our distance sufficient? Well, in this case, we have 200 millimeters. But there might be also a possibility that we could reach over the light curtain. Here we look to the dimensions. This table looks very similar to what you might find in 13857 for reach over of a guard. But here we're trying to reach over the top beam of a light curtain. So here we have A, which is the height of the hazard, or B, which is height of the top detection zone, so the height of the top beam of the light curtain. And then what we have is another factor, what we're going to call CRO. The additional distance a body part can be moved towards the hazard before actuating the safeguard. What we're going to end up doing is that depending on the height of the presence sensing device and the height of the hazard, if I'm able to reach over the presence sensing device, we may have to add an additional distance to where I can't reach over the presence sensing device to the hazard. So that's what our CRO is. And then yet, our S is still our minimum distance. I'm going to say distance. Here, there's a table very similar to 13857. In this case, it's 13855. It's in 13855. So here we have the height of the upper edge of the light curtain, which was 1,000 millimeters. So we select that. And then the current safe distance. Height of the hazard is 1,000 millimeters, and the height of the upper edge is also 1,000 millimeters. To find out where those two cross, our CRO comes out to 1,150 millimeters. So from here, what we end up doing is we take our S, which our stop time calculation was 200 millimeters, and we add the 1150 from the reach over of the light curtain. So our total safe distance is 1,350. Our current safe distance of 1,000 millimeters is not sufficient. So to mediate this, you could easily install a taller light curtain, or you move the light curtain closer. That way you cannot reach over. We also have different approaches for indirect approach. So depending on where the hazard may lie, you could just add up the distances, shortest distances to the hazard, to possibly align for an indirect approach. You see in the top example, you might have the hazard which is beyond 4. So that's line 2, which is an indirect approach. You would add up S1, S2, and S3, depending on the distances. Next, we can start looking at laser scanners, which operates on a time of flight theory. A beam of light is pulsed out from the receiver, and it looks for similarities within the scans. It finds a dissimilarity between the program scanning area it will trip the outputs. So here, typically like we like to see in a laser scanner application, is at least the floor painted or outlined based off the projection field on where the scanning area is. It's a very good good engineering best practice. We also see laser scanners on automated guided vehicles, AGVs, as they're referred to. When it comes to laser scanners, we use the equation 1600 millimeters times the total stop time plus 1200 minus 0.4h. But the other thing we have to look at is the lowest permitted height of the protected field, where h might be equal to 15 times the resolution minus 50. So your maximum height may be 1000 millimeters. System response time must be considered when defining T. So look to your manufacturer-specific response time. In this example, they use 80 milliseconds. Here, depending on the height, determines the protective field. We could also mount our laser scanners on an angle. So here, mounting it on an angle, we'll have we'll be able to detect them at an earlier state. Where you see here in case 1, with it mounting very easily at the person's ankles, what happens is that you can reach over. The higher the laser scanner is mounted, the more likely it is to detect you. Here, we have an example of laser scanner. The resolution of the scan is 70 millimeters. The height of the scanner is 30 millimeters off the ground. And the stop time of the machine is 100 milliseconds, and the response time of the scanner is 80 milliseconds. Our current safe distance is 1000 millimeters. Here we can do our equation. We have 1600 millimeters times our 1200 minus 0.4h, 1600 times 180 milliseconds. Current height is 30 millimeters. We get a total of 1,476 millimeters. Based off our current safe distance of 1,000 millimeters, our safe distance is not sufficient. In this case, you may have to either get a different laser scanner that can have a tighter resolution, such as something that may scan at 50 millimeters or even 40, or you're going to have to increase the safe scan distance on the laser scanner. OSHA's calculation is very similar to ISO 13855, but here they use a constant of 63 inches per minute. 63 inches per second, along with TF, which is the total stop time of the overall system. Maintain, which is what they refer to as DS. Distance between the light curtain or scanner to the danger point. ANSI also has its equation, where DS is the safe distance, K is our constant, which is 63 inches per second, or 1600 millimeters per second. Here they use a couple of different T factors, as they call them. They have TS, which is the stop time of the machine, TC, which is the response time of the control circuit to active machine stoppage, DR, which is the light current response time, DBM, additional stopping time attributed to the response time of a brake monitor. So something along the lines of a press may have a TBM. Instead of having a C factor, ANSI uses a DPH, which is a depth of penetration factor. So here it's 3.4 times the resolution, which they define as OS minus 0.275. This is all done in inches. or 13855 uses millimeters. We have different ways to go through and verify and validate our systems. Or it's two-part, an evaluation of the installation of compliance with the installation requirements, basically ensuring the presence sensing device may not be easily circumvented. Then we also have to have a confirmation on the safe distance. Through an actual measure of stop time, we calculate the required safe distance and compare it to the actual. So how do we actually verify our safe distance? Well, there's different types of encoders that you can also purchase and use. So here's two examples. ASM, they have the NMG2, which is a stop time measuring tool, which basically is a string encoder. You place the string on the end of a robot, for example, and then you break the light curtain, and based off the light curtain breaking, you can measure the safe distance based off how far the string encoder falls out. There's also the micro STM. There's also a string type of encoder. Those are available for you to purchase on the market. But one of the other popular methods that is commonly used is a video camera method. So here we take a video of the stopping event. We include the state of the safeguard, the initiating stop signal. We have some kind of analysis where we count frame by frame for the total stop time. What do we do? Your average digital camera shoots at about 30 frames per second. There's plenty of other ones that are out there that shoot at 60, even 120. So here, we'll shoot at 30 frames per second, which is equivalent to 33.3 milliseconds. We typically use a tripod to maintain we can have steady responses, consistent videos. Well, I also have some kind of video analysis software. So here we need to determine the hazardous location. We need to measure the safe distance, determine the critical motions at high speed. So if you're using a robot cell, you need to have the robot moving at full speed under full load. That includes your end-of-arm tooling with the part that it has inside of it. You need to be able to maintain the presence sensing device and the robot stopping in the same frame. We're going to analyze the frame by frame, and we'll determine our depth of penetration and calculate out our safe distance. Then compare it to our actual safe distance we have. So here, what happens when you use a video method is that you have to have there's going to be a little bit of an error correction. Because the machine could stop in between frames. So in this case, that's 33.3 milliseconds. That could be a decent amount of time depending on where you stop. So we use an error correction. In this case, you can see the stop event triggered between two frames. The zero speed was reached before it reached the next a full frame. What we do is when we have the stop event, we look for the LEDs on the light curtain to change state, which typically happens between frames 0 and 1. That's where we start counting our first frame. And the zero speed happens between frames 6 and 7. Here we count as 7. So in this case, where we first see motion, or where the LED on the light curtain has changed state, that's our first frame. Then the last frame that we see motion in is our last frame. So here, red LED was first noticed on frame 1, therefore the stop event happened between 0 and 1. Machine shows no relative motion between frames 7 and 8, therefore zero speed was reached between frames 6 and 7. Presence sensing device comes on after the presence sensing device response time. Therefore, the presence sensing response time must be added to the stop time measurement. Here we have our analysis software. There's several different programs out there that can do it. In this case, they're using Windows Media Player. I often use VLC Media Player. Here what we do is we set up the video to be able to see the light curtain. We break the light curtain to see our hazardous motion. That way we can see the dangerous motion frame by frame until it shows no more movement. Now what we also want to do is we want to repeat the test to make sure we get consistent results. So on average, I typically will do a test 3 or 4 times to make sure I have consistent, repeatable results. If the results aren't repeatable, you may have external factors affecting your stop time. It may require additional analysis on the machine. But in this case, I did my test 4 times where I had stop times of 19, 20, 20, and 21 frames. What I'm going to do is I'm going to average those together. My average is 20 frames. So the initial frame stops I will have is 20. If I can convert that 20 frames over 1 second for 30 frames, I get a stop time of 0.67 seconds for the response of the control system and the machine stopping. But I also have to add in the response time of my present sensing device. In this case, the light curtain had a response time of 20 milliseconds. So I add those two together, I get 0.69 seconds. So here, my light curtain, I'm going to use a calculation of, my K is 2,000 millimeters. My C is 8 times D minus 14. My stop time is 690 seconds with a resolution of 40 millimeters. So if I crunch my numbers, I get 1,588 millimeters. Puts me beyond my 500 millimeters requirement, so I can use 1,600 millimeters to crunch the numbers. Once I do that, my total stop time and safe distance is 1,312 millimeters. The reason why we went from the 2,000 to 1,600 is because I am beyond that 500 millimeter mark. So I am only required to use 1,600 millimeters to actually shorten the distance up by over 200 millimeters. From here, I'm going to kick it back over to Stephanie.
Thank you, Dan. That was an excellent presentation. A few of you have already submitted questions, so we're going to jump right in. While our presenters are answering your questions, please take a moment to complete the feedback form that appears on the left side of your screen. Okay, question number 1. Why was S equals 1,320 millimeters not sufficient in that parallel setup calculation?
That was... So in this case, parallel approach of this example, 1320 is the total, is our safe distance. Our current safe distance was 1,000 millimeters. So what we were doing is we were verifying the current safe distance based off the calculation. So in this parallel approach, the 1,000 millimeters that was currently used was not sufficient because the distance from when I break the light curtain to the machine stop, I could still reach it. So based off our current safe distance compared to the calculated safe distance, we need to move it back an extra 320 millimeters.
Where does this formula calculation come from?
All the formulas are in either ISO 13855, or you could look to the ANSI B1119 equation.
To specify, where does the scanner formula originate from? ISO?
Yeah, the scanner formula we use is out of ISO 13855.
Can you go through how to observe and time the actual system stopping time for use in calculating S when using area scanners?
When using area scanners, what you do is we typically watch you'll see an LED typically on the area scanner. You watch that to change. And from there, you need to be able to watch the dangerous motion also in the same frame. So based off the area scanner, you may have to have a little fancy photography with a camera and a tripod. I've tried using my iPhone several times. Yeah, my iPhone can shoot at 60 frames per second, but to be able to hold it still for a long enough time to do consistent results gets very hard. So I really depend on the zoom and the tripod to do stop time verification.
What about light curtains that are already in place? Are we to recalculate and set those light curtains based on today's recommended webinar?
Typically, a lot of times when I do risk assessments, I'm always going to verify the current safe distance of any type of work cell or machine I do. And sometimes, they are ballpark. You may be off a couple of millimeters here or a couple of inches here or there. And a lot of times, some engineers don't understand stop time, and based off the size of the cell, what they've done is they just placed the light curtains where they felt they needed them. And a lot of times I have found that they are severely not in the proper location. But because of space and real estate obligations within factories that have already been there for a long time, they're not able to move them.
What reference do you use in determining how to calculate stop time? Where does 20 ms come from for our correction factors?
All the correction factors are all all the C factors and all that are all dictated out ISO 13855. The standard gives you very good guidance on what to use. What we did here in this presentation is we summed up the charts like this, just like as we see here. This is the parallel approach. We just summarize. It's very easy to summarize at least the parallel or the normal approach, which is the parallel light curtain, based off the resolution. CRO can also be easily added into this for the additional safe distance required to reach over.
Okay. Well, we still have time for some questions, so if you have any lingering questions, please feel free to put them into the question box on the side of your screen. Let's see here. There's some questions coming in, and while we're waiting for them to come in, Dan, here's a question. Can you clarify the depth of penetration? How is it determined, and can it be preset?
So depth of penetration, or at least the ANSI equations, or even the C factor in 13855. They're very, very similar factors. What is hard is when you start designing machines where you have to start getting off, theoretical safe distances. If you're doing a robot cell, it's typically pretty easy because the manufacturers of the robots will give you average stop times for the robots under different loads. But when you start getting into custom machinery, based off mass and inertia, it's to be very hard to calculate out safe time. A lot of times, you can over-design and then possibly shrink guarding up later, or sometimes even with doing mechanical guarding with a light curtain. Some of the machine manufacturers that I've dealt with, we physically have to wait till the machine's running in order to actually dictate out the safe distance accurately.
Do you have to calculate stop time using all three ANSI, ISO, and OSHA methods and choose the most conservative results?
The minimum that you have to meet, at least here in the United States, is the OSHA equation. But based off the OSHA equation, it's so similar to the ANSI and the ISO. With the ANSI and the ISO both being voluntary consensus standards, either one is typically acceptable. I tend to default to the 13855 equations. when I do risk assessments because the ISO 13855 has the additional factor of reach over, the CRO factor, where ANSI does not. So I tend to like to use that factor just makes the machine a little bit safer.
Okay. How often have you seen OSHA ask to verify safe distances that are being used?
I haven't heard of a case that they have actually asked, my experience, but I have met other colleagues that have required safe distance calculation based off somebody walking in through a light curtain and getting struck by a moving object or a hazard. So they do require it, just depends on the incident.
Okay. Do you have any additional comments, Dan, while we wait another minute for any last-minute questions to come in?
Currently, especially with doing stop time, we did the most popular, which are light curtains and laser scanners. Stop time analysis is also required for things like interlock guards. You're able to open an interlock guard and reach the hazard before it stops. There's other possible, that's something you have to worry about. So there's either one of two things: put a guard lock on it, or you need to increase the distance between the interlock guard and the hazard. It's also required for things like safety mats. So if you step onto a safety mat, the equations are very similar to that of a light curtain or to a laser scanner for a safety mat. And then things like two-hand control. Safe distance calculations are also needed for things like two-hand control. Your hand closest to the hazard needs to be calculated out to make sure you can't release the two-hand control and reach into the hazard of, say, a press. And those other things such as like a safe vision system where stop time is also required. Here it's virtually a three-dimensional laser scanner, which in all reality it's a camera system that's being compared with fixed reference points on the ground. Typically anywhere from 40 or 70 millimeter resolutions. So it's basically a 3D laser scanner, a three-dimensional laser scanner that's using cameras. That is also another application where stop time analysis is required.
Okay. For anybody wondering how you can receive a copy of today's PDF slideshow, it is available in the resource list in your webinar browser. All right. Let's see here. Can you please take a minute to explain the approach speed and depth of penetration approach table?
So here, the speed and depth of penetration. So the first one, and this here we're using, it's for the perpendicular approach for vertical light curtains. You'll see the first part of the resolution. If the resolution is less than 40 millimeters, so typically a 14 millimeter, which is finger detection, or a 30 millimeter light curtain, which is hand detection. You use the top equation there, which is 2,000 times T plus 8 times D minus 14, where it cannot be equal to 0, for anything that is between 100 millimeters and 500 millimeters. So it accounts for hand-arm speed, for relatively being close. Go right below that. And if you are at a distance greater than 500 millimeters, you use 1600 as your constant speed. If you go to resolutions between 40 and 70, we still have our 1600 times T, but our C factor, or depth of penetration, is increased to 850 millimeters because of less detection. There's a greater distance between the beams. Then we can go down to multi-beam systems where we still use the 1600 times T plus 850. They give you recommended beam heights depending on the number of beams. And if we use a single beam system, our depth of penetration is increased to 1200 millimeters with with a recommended height of 750 millimeters. But yet you should also justify the resolution of your light curtain through your risk assessment.
Let's see, next question. This one says, I hate to argue with the expert on what to do if the light curtain safe distance is incorrect, but I see it as different. OSHA has a certain light curtain formula. This is not as conservative as an ISO or ANSI formula, but is legal requirement. If you injure somebody because if somebody's injured because their light curtain is too close, you're in violation. So if you're too close, you need to decrease the stop speed or move the curtain. Do you have any comments on that?
It's absolutely true. If the light curtain is too close, you do have to move the light curtain farther out or somehow make sure the machine stops faster. In a lot of cases where I have found that in existing manufacturers, they don't have the room to move the light curtains out farther. So what they do is they actually are willing to accept the risk, just as B11.0 or ISO 12100 state, is that they are willing, you reduce the risk to your as low as reasonably practical values of what you're willing to accept or tolerate. And I have found that in industry, in existing facilities that have had light curtains installed.
Okay, we have time for one or two more questions. Okay, how do you apply stop time to press brakes?
So the press brake, what you have to worry about is the downstroke on presses. The press standards don't consider the upward stroke as a dangerous motion, but they make specific type stop time analysis devices for presses, mechanical presses, even press brakes. Then the other thing you also have to worry about within the press brake standards is that we do have to have press brake monitoring devices for American presses. They're not required in Europe or the international standards, but they are required here per the ANSI standard.
Okay, is there a minimum stopping distance even after you calculate S? We used video to obtain system stop time and calculated S as 15 inches, but that seemed too close to the robot from a safety perspective.
If you're the only ISO 13855 dictates a minimum of 100 millimeters as the bare minimum, which is equivalent to roughly 4 inches. I would recommend repeating the test again. And if you're consistently getting 15 inches, that would be the stop time for the device then. If you're getting consistent results, but make sure it's at full speed and under full load. You don't want to be doing a robot that's a pick and place without the, say a 5-pound bag of dog food in it. You want to make sure it's at full load at full speed.
Okay. I'm afraid we're out of time. I'd like to thank our presenter, Dan, and our sponsor, Pills. As a reminder, if you're registered as a group, please add the names and emails of all in attendance on the exit survey. On behalf of EHS Today, have a productive remainder of the day.